disubstituted cyclohexane, meaning that you got two substitutions. So let's draw for cis 1,2 dimethyl cyclohexane. How are you going to draw them? Well, cyclohexane, so it got to be 6-member ring, right? Two methyl groups, CH2, CH2, and CH3, CH3. Two methyl groups should be right next to each other. But not only that, I give this specific geometric isomerism you're going to draw, which is a cis. They have to be right next to each other, right, on the same side. They both can be down, they both can be up. There's two possible ways to draw them. But let's talk about just this one. Two methyls both happen to be connected with a wedge line. They both stay above the plane. That is not the chair conflict. You know, that's just how to draw the cyclohexane with loose structures or lining point. These are not chair conformation. When I ask you to draw the chair conformation, you got to draw the chair, right? Chair like this. It could be the other form, but doesn't matter. We still have to talk about chair interconvergence. You're going to bound to draw the other one anyway. So let's draw the chair conformation like this. And then I told you this is the equatorial bond of that carbon. That's the axial of this carbon. That's equatorial, that's axial. Question comes, where should we put the methyl groups? The methyl goes here, here the methyl goes down there. What is going to be cis? They're not exactly right next to each other. When you draw like this, these two are right next to each other. You can easily see that that's cis. When you draw the chair here, they should be putting one here, one down there, so they can be right next to each other. Will that be cis? Or should we put one here or one there? So drawing the chair from that structures is not trivial. You got to think about their relationship. So let me tell you what I do. There is a CH3 taking an upper position on this carbon. There's a hydrogen is there, which we didn't draw, but that must be connected with the dash line. So when you compare the hydrogen and the methyl groups, we are saying that methyl taking a higher position, right? Upper position. So whenever I put the methyl groups here, then I put the methyl upper position compared to that one. So I'm going to talk about this one and that one only. Methyl's up, hydrogen is down, right? Go for the second one. I put the methyls up, hydrogen down. So relative positions. These are the higher position compared to that one. That's the higher position compared to the other one. There's upper position, lower position, upper position, lower position. They may look different way because of their being a chair, actually equatorial, but relative orientation doesn't change. These two still both taking upper side of the substituents. So these are how you draw the cis 1,2 dimethyl cyclohexane. This is the upside compared to that one. That's the upper side compared to the other one. Both are the upper side. There must be cis 1,2 dimethyl cyclohexane. So that's what you need to do to draw the chair conformation first. When you draw the one chair, you should do the other chair by flipping the corner, right? That's a chair interconvergence. How to convert the chair? One corner goes up, the other corner goes down, right? That's how that's going to happen. This corner goes up, the other corner goes down, then you get the other chair conformations. Again, that will have this is carbon number 1, that's carbon number 2, but still things doesn't change. Something that stays upper position has to stay the upper position compared to that. Something that has an upper position has to upper position compared to the other one. So we just have convert the chair into conversion. We didn't break the isomers together. So that's the other chair conformation drawn from this one by just flipping the corner down, but that makes it axial, right? Becomes the equatorial, and the equatorial one becomes an axial by flipping the chair. these two conformations, if you compare which ones are more stable than the other, easiest way to do it is count how many axial substitutions. Because the axial substitution raise energy. Equatorial substitutions doesn't raise energy. So equatorial one's fine. How many axial conformations are there? That's critical. You got one axial conformation with this chair conformation. You got the other chair conformation, still have one axial substitutions. So in both are going to be the same energy because axial is a one raised energy. You got one each in both chair conformations. So these two are equal energies. So what that means is chair conformation of this one can be drawn this way or can be drawn the other way because they're going to be just equally populated. So is everything going to be this way? Well, I'll show you. I'm going to go every possibility. Normally, the rest of them is going to be your homework, but I'm being very kind to you. I'm going to show all of them. I don't know how fast I'm going to do it, but let's do it and see how things go. It's still the 1, 2. What I change is the trends. All right? Trends means that they should be opposite each other. One method up, the other method down. Right? First task is how to draw the chair conformation. Again, you're going to draw the chair like this. You're going to show the where the equatorial one, where the axial one, axial, equatorial. You're going to do that. Then you're going to figure out where the method is going to go. If that's the problem number 1, which you make this one, the methyl is taking an upper position compared to the hydrogen of its own. So this is upper side compared to that one. So methyl should go to the equatorial one. The other one, methyls are taking a down position, right? It's a dash. There's a hydrogen must be there with a wedge bond, which is not shown. So methyl on the carbon number 2 should take a down position, not upper positions. So this is the upper position, that's a down position. So CH3 of the trans, that goes to the equatorial position. Because we are drawing trends, not cis. So that's the one of the chair conformation. You see already that these methyls are equatorial, the other methyls are equatorial. Both are not raising any energy. When you flip the chair, this corner goes up, the other corner goes down. Now you probably know that what's in the equatorial, they goes an axial, because that has to be opposite to the other one. So these corners goes up, and that method hydrogen's over here. This equatorial is going to go down, being an axial from the equatorial, and hydrogen's there. The other chair conformation drawn by the chair convergence have a 2 methyl, both axial. If you compare these two, you can easily say that this is a lower energy compared to the other one, because that one has a lower axial substituents. This one is a 2 axial substituents. 2 axial means you got the 4 Cauchy interactions, which is a 4 kilocalories higher. So if I ask to draw what is the most stable chair conformation of the trans 1, 2 cyclohexane, you're going to draw this, not the other one. Or you shouldn't draw the cis conformation either, right? Because I asked you to draw the trans. There's many things can go wrong. Not drawing chair properly, or not flipping the chair properly, not comparing them properly. So this is probably the most hard part, and this is something that you're going to study for the quiz 1 and test 1. Let's talk about 1,3. 1,3 means that now you got the 1,3 position, not right next to each other. Is it going to be exactly the same as a 1, 2? No. You're going to see that the way we do it going to be the same, but the way where they're going to be landed down is different. That's why I'm showing you all of them. Cyclohexane with the 1 and 3 dimethyl, but we're going to draw the cis because I asked you to draw the cis. That's how does it look like, the loose structures, then how it's going to be the chair conformation is something that you need to figure out. But this one, again, the same thing. The CH3 and hydrogen because it's a wedge, hydrogen is a dash. Methyl should take the upper side compared to the hydrogen. For the carbon number 3, methyl is the wedge. So methyl should take the upper side compared to the hydrogen. This is carbon number 1 and 3. That is the upper side compared to that. This is the upper side compared to the other one. So 2-methyl should be on axial substitutions for that chair conformation. That's cis 1,3 dimethyl cyclohexane. Chair interconvert by raising these corners up and raising the other corners down. By raising this one up, that's H3 in the upper side, still going to be in the upper side. What that means is that it's going to be in the equatorial positions. That axial substituents is going to be flipping down, but still taking an upper side because we put in the wedge there. That's still taking upper side, and then that's taking equatorial positions. So again, axial becomes equatorial, axial becomes equatorial, whenever you change the conformation. Which one is the most stable? The one with the less number of axial is the most stable, right? More number of equatorial. So this is the most stable chair conformation of the 1,3 cis dimethyl cyclohexane. What about trans? Trans, 6 member in there, 1 up, 1 down. Let's draw the chair conformation the same way. First carbon, third carbon. I draw the line, whether axial, whether equatorial, axial, equatorial. Only thing that you need to worry about, put the methyls so they can be trans. One has to be taken on upper side compared to the hydrogen of its own. So this is up, that's down. So CH3 must go up here. The other one, methyl should taking a lower side, right? Because of that with a dash. Hydrogen, which is not shown, is the upper side. So this is the upside, this downside, that's the methyl of this one. This methyl is the upside of that one. So that is a trans 1,3 dimethyl cyclohexane. You see here, one taking an axial, the other is an equatorial. But we have to draw the other chair conformation just to say that how they're going to look like when the chair interconvert. When this chair interconvert to the other form, axial becomes equatorial, right? Equatorial becomes an axial. So if you look at that, how many axial substituents for each substituents? One here, one there. It's just different method becomes equatorial. But because the same number of the axial substituents, we can say that both are the same energy. So when I ask you to draw the chair, most stable chair conformation of the trans 1,3 dimethyl cyclohexane, you can give me either because both are the same energy level. Now there's 2 left, 1, 4. Cis and trans. We're both going to do it. I know it's kind of long, but I'm doing this for you. Normally, I didn't do it at all, but I'm doing this for you because a lot of people make a mistake. I just want you to see that what's the right way to do it. Cis 1, 4. That's something we're going to draw. Cis 1, 4. 6 member ring, both methyls the same side, 1, 4 positions. We're going to draw the chair conformation of that. This is chair, this is the carbon number 1, that's carbon number 4. We put the methyls taking an upper position on both carbons. So whenever we populate the methyls on these 2 carbons, that's upside compared to the other one, methyl should go here. That's upside compared to the other one, the methyl should go there, right? That's how you get the 1, 4 cis dimethyl cyclohexane. That has a 1 axial substitute of 1 equatorial. That chair conformation will fit into the other chair conformation by raising these corners up, raising the other corners down. That's going to make this equatorial goes an axial because that has to take the upper side. That axial will become equatorial because that's the upper side compared to the hydrogens. In a way that axial becomes equatorial, equatorial becomes an axial. So if you look at the number of the axial substituents for each chair conformation, they're the same number. 1 methyl always stay in an axial, even though they're different methyl. This was an axial in this conformation. that hydrogen becomes an axial for the other conformation. So you can say that both are the same energy. But when I ask you to draw the whole stable shell conformation of the trans 1,4 dimethyl cyclohexane, the two methyl should be opposite to each other, one up, one down, right? If you draw the shell conformation again, this is a shell conformation that this is the upside compared to the other one. I'm talking about this one, taking upper side compared to the hydrogen that's shown here. So this must be the methyl here. And then carbon number 4, the methyls take your downside compared to the hydrogen should be shown in the wedge. Even though it's not shown, it's there. You just don't draw the hydrogen, right? That's why the hydrogen is here with wedge. So methyls should take the downside compared to the hydrogen. That's the upper side, that's downside. So two methyl goes on the equatorial side. That's the water shell conformation. By raising these corners up, by raising corner down, this equatorial will become an axial. That equatorial becomes an axial. So both will be axial. So those two are not in the same energy. You still need the number of axial substituents. This has a 0, that has 2. So which ones are low in energy? That one. So which ones are most stable shell conformation of the 1,4 trans cyclohexane? This one.